Have you ever stopped to think about how the digital world actually works? I mean, really works? Behind every single app you use, every website you visit, there's a data system making millions of choices a second. But here's the thing, it's not magic. It's all built on a series of critical and often invisible trade-offs. So let's pull back the curtain and really get into the architect's guide to those choices. Here's a perfect example. Think about your bank account. The balance has to be correct, right? Down to the penny all the time. But your social media feed? Well, if you see a post from a few minutes ago instead of a few seconds ago, it's not the end of the world. And that's not a bug, you see. That's a deliberate choice about what that system decided was most important. And that right there is the key to everything we're talking about today. Every data system is the result of a deliberate trade-off. And to really get our heads around why our apps and services behave the way they do, we're going to walk through the 3 essential questions that every data architect has to answer before they write even a single line of code. All right, first up, the big one. How perfect, how absolutely correct does our data need to be right this second? This single question sets up the ultimate tug of war in data systems, the constant fight between being perfectly correct and being always on, always available. See, when you absolutely positively cannot be wrong, you need something called an ACID transaction. Think of it as a sacred vow for your data. It's an all-or-nothing promise. When you transfer money, the system guarantees that the money is either fully taken from your account and fully added to the other, or the whole thing fails and it's like it never happened. There is absolutely no in-between. It's the gold standard for banking, e-commerce, you name it. And this really splits the database world into 2 big camps. On one side, you have your traditional relational databases. They live and die by those ACID rules, giving you unbeatable correctness. But on the other side, you've got NoSQL databases, which were built for one thing: insane scale and speed. And how do they do it? By loosening up on those strict correctness rules. That's why they're perfect for social media feeds or sensor data, where being fast and online is just way more important than being perfect. And look, this isn't just a matter of preference. It's basically a law of physics for distributed systems, and it's called the CAP theorem. It says that when the network connection between 2 servers breaks, which is called a partition, you are forced to make a choice. You can either choose consistency, which means you might have to stop responding until you can guarantee the data is the absolute latest version, or you can choose availability, which means you always give a response, even if it's with slightly stale data. You cannot have both at the same time during a partition. You have to pick one. So, what happens when you pick availability? Well, you get a model called Eventual Consistency. And the promise it makes is, well, it can be surprisingly weak, as this quote shows. It's basically saying that if everyone just stops making changes for a while, the system will eventually sort itself out, and all the servers will agree on the right value. It's a promise that something good will happen, eventually. So how on earth do you build a real-world business on a promise that flimsy? You have to plan for mistakes. You build in something called compensation. The best example is an ATM. A bank would rather an ATM give you cash even if it's temporarily offline. That's choosing availability, and risk you overdrafting. Why? Because they have a way to fix it later in the real world. They charge an overdraft fee. That fee is the compensation that retroactively fixes the data inconsistency. Okay, on to our second question. This one builds on what we've just talked about. It's not enough to just be fast. You have to be fast for the right kind of job. This gets into the trade-off between raw speed and the specific type of work or workload a system is built to do. Data systems are usually really good at one of 2 things. First, there's OLTP, or online transaction processing. Think tons of tiny, rapid updates, like processing a credit card payment. This is all about write speed. And then there's OAP, or online analytical processing. This is for crunching massive amounts of data to find insights, like generating a huge quarterly sales report. It's all about read speed. And here's the catch. You can't be the absolute best at both. Let's make this real. Check this out. In a benchmark that tests simple, high-frequency transactions, a classic OLTP job, MySQL just blows the doors off, handling a much higher throughput. It's an engine that's literally built for that kind of velocity. But watch what happens when we flip the script and change the workload. Now we're looking at complex analytical queries, an OLAP workload, and boom, the tables are completely turned. PostgreSQL's more sophisticated query planner absolutely shines here, finishing the job in less than 1/3 of the time. This is exactly why asking which database is faster is the wrong question. The right question is always faster for what? And this same idea applies right down to how the data is physically shaped. Key value stores, they're basically like a dictionary. They are unbelievably fast at finding one specific thing, like finding a needle in a haystack. On the other hand, columnar databases are structured more like a spreadsheet. They are purpose-built to scan entire columns at lightning speed, which is perfect for analyzing the whole haystack. Different data shapes for different kinds of speed. But, of course, speed isn't free. Faster storage costs more money. So to get around this, modern systems do something really clever called automated data tiering. Any data that's being used all the time, we call that hot data, gets to live on the expensive, super fast storage. But as that data gets older and is used less, it automatically gets moved to cheaper, slower, cold storage. It's a brilliant way to manage costs without anyone even noticing. So we've talked about being perfect, and we've talked about being fast. For our final question, we need to zoom all the way out and look at the blueprint for the entire system. How do we organize all this data? This is the big architectural trade-off between having one central point of control and having a decentralized system that can scale. The way we build these systems has been on a really fascinating journey. For decades, the standard was the data warehouse. Think of it as a pristine, highly curated library for business data. But it was expensive and inflexible, often becoming a bottleneck. So the pendulum swung hard in the other direction, to the data lake, just a giant cheap pool to dump all your raw data into. But that freedom often turned into chaos, creating what people call a data swamp. Now, the future seems to be a hybrid, the data lakehouse. The data lakehouse is this really powerful modern compromise. It's a brilliant piece of engineering that lets you apply those reliable warehouse-like features, things like ACID transactions and data quality checks, directly onto raw files sitting in cheap cloud storage. It bridges that huge gap between the flexibility of a lake and the reliability of a warehouse. It's kind of like having your cake and eating it too. But for really big companies, even a lakehouse can become a bottleneck if it's all managed by one central team. And that has led to a pretty radical new idea called the data mesh. And here's the most important part. This isn't just a new technology, it's a shift in how the organization works. Instead of one central team owning all the data, it says data should be treated like a product, owned by the teams that actually create it and know it best. The marketing team owns the marketing data, the sales team owns the sales data, and so on. Now that sounds like a recipe for total chaos, doesn't it? So how do you stop it from becoming a complete free-for-all? The solution has this incredibly complex-sounding name, but the idea behind it is actually pretty elegant. Federated computational governance. Let's break that down. Federated means individual teams own their data, but they have to follow a set of global rules. Computational means those rules for things like quality and security aren't just in a document somewhere. They're enforced automatically, as code. It's a system designed to give teams freedom and autonomy without sacrificing the standards the whole company needs. Okay, wow, we have covered a lot of ground. Correctness, speed, organization. So let's bring it all home and put it together into a simple, powerful framework you can use to think about any data system. It all comes back to our three questions. Number one, how perfect must it be? That forces the choice between consistency and availability. Number two, how fast must it be? That determines if you're building for small, frequent transactions or massive analytical queries. And number three, how organized must it be? And that guides whether you need a centralized warehouse or a decentralized mesh. Literally, every data system you've ever used is an answer to these three questions. So if you only take one single thing away from all of this, please let it be this. There is no such thing as the best database. There is no best architecture. There are only trade-offs. The most brilliant, perfect system for a bank would be an absolutely terrible choice for a social network, and vice versa. The right choice, the optimal choice, is always dependent on the specific problem you are trying to solve. And that leaves us with one last thing to chew on. We are right now entering an era where AI and machine learning are creating completely new, unprecedented demands on our data. They often need speed, scale, and correctness all at the same time. So the question is, which of these fundamental trade-offs, these rules that have defined data systems for decades, do you think will be the first one to break?